Hey guys, this is the start of Unit 7. We are doing 7.1 Systems of Linear Equations with two variables. So when it comes to systems of equations, you've got three possibilities, three types of solutions or systems you could have. The system could be independent, and that happens if the lines intersect at exactly one point, which gives a single ordered pair solution of the system. That was a lot of words. So basically, if you've got two lines that intersect at one point, like so, one point, that one point is your solution, and so the system is independent. Okay, and then your system is considered inconsistent if the lines are parallel, which means there is no solution because the lines do not intersect. The solution set is the empty set. There is no solution. So if my lines are parallel, like so, there's no intersection, and we know that where two lines cross is the solution. Where the two lines intersect is the solution, and so since parallel lines never intersect, there is no solution, and we call that system inconsistent. And then case 3, the system is dependent. And that is if the graphs are the same line, which gives an infinite number of solutions. Well, if the solution is the point where the lines intersect, and on this example, my lines, there's one of them, there's the other one, they're right on top of each other, I'm going to have infinitely many points where those lines intersect. They are intersecting at every single point. So you have infinitely many solutions, and that is called dependent. Let's solve a system of equations by graphing. So I'm going to pull up my calculator here. I'm going to be putting both of those in y1 and y2, and then I'm going to see where the two lines cross. In order to put them in y equals, I need to solve for y on both of them. So just taking the first equation, 2x minus 5y equals negative 25, and solving for y. So subtract the 2x. And divide by negative 5. Everything gets divided by negative 5. So y equals 2 over 5x plus 5. So I'll put that one in y1. And then the second one, solving for y on that one. Add the 4x. Divide everything by 5. So you get y equals 4/5 x plus 35 divided by 5 is 7. All right, so we're going to put these two equations in the calculator. Okay, and the next one was 4/5 x plus 7. Let's look at our graph. All right, so there's my two lines, and you can see that they cross at exactly one point. So this is going to be considered an independent system. An independent system because the lines cross at exactly one point, so there's exactly one solution. Now to get that solution, you could eyeball it, but I wouldn't recommend. So do second calc, which is the trace button. And then 5 says intersect. We want to know where they intersect, so it makes sense. So second calc 5, and then just hit enter 3 times until it says intersection. So your intersection happens at -5, +3. So that is your solution. -5, +3. There you go. In the calculator, looking for that point where the 2 lines intersect to get the solution. Now let's look how we can solve using substitution. So to solve the system by using substitution, the first thing you want to do is isolate one of your variables. It's always easiest to isolate the variable that has a 1 as a coefficient, if that does exist. In this case, it would be the y in the second equation, because it already has a 1 as the coefficient. So all I have to do is add the x to the other side, and I have y equals x plus 3. So again, what you're trying to do is solve for one variable, either one, in either equation. The next part is the actual substitution. So you're going to take this x plus 3, and because it equals y, you're going to substitute that in for y in the other equation. So I'm replacing that y with x plus 3 because it equals y. Y equals x plus 3, so I can literally replace that y with x plus 3. So 3x plus 2, parentheses, instead of y, I'm putting x plus 3 equals 11. And now we can solve for x, because the only variable left in this equation after the substitution is x. We can now use this equation to solve for x. So distribute the 2. Combine like terms. Subtract that 6 over. Divide by 5. X equals 1. Well, your solution is not just the value of x. Remember, your solution is the point where the 2 lines intersect. And so we need to have a y value as well. So we'll take that x and we'll plug it back into either equation to solve for y. I'm actually going to substitute that x back into this equation just because that one already has y equals. So since I'm looking for y, that's going to be the easiest option. But like I said, you can plug that x back into any of the equations that you have. So y equals 1 plus 3, 4. Okay, so now your solution, which is the point where the 2 lines intersect, is going to be 1, 4. You can check that in the calculator just by checking to see where the 2 lines cross. So that is substitution. There's another method for solving equations algebraically, a system of 2 equations, and that is elimination. So for elimination, what you're trying to do is eliminate one of the variables. You do that by multiplying one or both of the equations by a number that will make the coefficients of one of the variables match. So let's just look at it just to see how it works. So to make one of the coefficients match, I could multiply the first equation by 2 and the second one by 3. And that will make my coefficient on x match, because I'll have 2 times 3 is 6 and 3 times 2 is 6. You actually want the signs to be opposite, so I'm going to actually change this to a -2. So that the coefficient on x in the first equation will be -6. The coefficient on x in the second equation will be +6. So you want them to be the same number, but opposite signs, just for one of the variables. Okay, so I'm going to go ahead and do that. You need to distribute the number you're multiplying by So the whole equation, because you need to multiply both sides of the equation by -2. Okay, so that becomes -6x plus 8y equals -2. And distributing this 3 to all the parts of the equation, I get 6x plus 9y equals 36. All right, once you've done that, you're going to add the two equations together. So the point of making these coefficients match but have opposite signs is that now when I add the two equations together, -6 plus 6 is 0. And so those two cancel out, which is where the elimination comes in. We've eliminated the x. We have eliminated the x. Okay, and then we add the 8 plus 9y gives us 17y. And then -2 plus 36 gives us 34. So now we're able to solve for y because we've eliminated the x. So we'll divide by 17. So y equals 2. Again, once you've got the y, you're going to plug that back into either equation just like we did with substitution. So plug that y back in for y in either equation to solve for x. So I've got 3x if I use the first equation minus 4 times 2 equals 1. So 3x minus 8 equals 1. Add the 8 over. 3x equals 9. Divide by 3. X equals 3. So your solution, aka the point where the two lines intersect, is 3, 2. X, y. 3, 2. And that is elimination. Now we're going to look at some special systems and we're going to practice using substitution and elimination again on these. Solve using substitution or elimination. Identify the system as independent, dependent, or inconsistent. So, but all of the ones we've solved so far have had one solution, right? So these have all been independent. Let's see what happens on these. On A, I would say the easiest way to solve this one would be by elimination. The reason is because there's no coefficient of 1 on any of my variables, and so it might just be easier to use elimination. Okay, so I'm going to multiply this first equation by 2 so that I have 6 and -6 as my coefficients on x. So that's 6x minus 4y equals 8. Don't forget, you're distributing that all the way across the equation. And then my second equation, I don't need to change at all. All right, now I'm going to add the two equations together. 6 minus 6 cancels. That was what we were going for. But I have -4y plus 4y also cancels, so all of that just equals 0. The other side, on the other hand, 8 plus 7 gives me 15. So if your variables both cancel, and you're left with something that is not true, we've talked about this before, 0 does not equal 15, then you have no solution. There's no point where those two lines intersect, which, if there's no point where the two lines cross, then they must be parallel. If you picture that on a graph, the lines have to be parallel if there's no solution. Well, that also tells you what type of system this is. It is inconsistent. When we have parallel lines, we have no solution. That is considered an inconsistent system. All right, let's do B. Okay, on this one, you could do elimination, but we just did that. So let's try doing substitution. We can solve for y here just by adding the 4x over. So y equals 4x plus 2. And then we'll substitute that in for y in the first equation. So 8x minus 2 times 4x plus 2 equals -4. And then we'll solve for x. So I've got 8x minus 8x minus 4 equals -4. 8x minus 8x, combining like terms there, those cancel. So I'm left with -4 equals -4, which you could add the 4 over if you wanted to, and get 0 equals 0. Either way, on this one, my variables cancel, but I'm left with something that is true. Those are both true. So if your variables cancel and you're left with something that is true, like 0 equals 0, -4 equals -4, then there are infinitely many solutions. And if there are infinite solutions, we know that means that the lines are actually the same line, and that is called dependent. The systems are dependent. They depend on one another. They are the same line. So if one line looks one way, the other one depends on that, it will also look the same way. All right, so those are your two special cases there, having the inconsistent and the dependent systems. What's a quick way to identify if a system is inconsistent or dependent? So this is a little trick you could use if you were taking a timed test such as the SAT, and they have it set up in standard form. Both of these systems are written in standard form. If you notice that one equation is just a multiple of the other, so looking at B, 8 is just -4 times -2. -2 is just 1 times -2. -4 is 2 times -2. So you can get that whole first equation just by multiplying the second equation by -2. So if you notice that one equation is a multiple of the other all the way across, that's going to be dependent. That's going to be the exact same line, right? Because if I multiply one of them to get the other one, then they're just the same line. However, if you notice that they're almost multiples of each other, but the constant on the other side right here on A, the 4 and the 7, does not apply. So for example, if I multiply the first equation by -2, it would give me the second equation, except for the constant at the end would be wrong. So if that happens, then it's going to be inconsistent, no solution. They're almost the same line, but the constant is wrong, so they're going to be parallel, but not the same line. So that would be no solution. So a quick way to identify if the systems are inconsistent or dependent is to check and see if they're multiples of each other. Check if the equations are multiples of each other. Okay, if they're multiples of each other all the way across, that's going to be your infinite solutions, your dependent system. If they're multiples almost all the way across, but not including the constant, then that's going to be inconsistent, no solution. All right, that's it for 7.1.